And we're plugged in, so I won't lose you guys. Other questions? We're about halfway through this. I mean, I know that we were about halfway through this problem. And I know that I think I verbally gave you the answer at the end, but I thought, well, I should probably go back and make sure that everybody's on board. So I'll come back down to the railgun again. Incidentally, these gray dots are supposed to represent the magnetic field coming out at you. And so it's apparently, I failed to mention that, but yes, the magnetic field is coming out at you. And as the projectile, the blue bar, moves down the rail, which direction is the induced current running through that blue bar? Again, it's an application of Lenz's law here. I want to know the direction of the current, not the magnitude. Get the magnitude, we have to apply Faraday. I just want the direction here. Yeah. What direction is the induced current through the loop as the bar moves down the rails? Or I guess a different way we could say this, well, no, I'll leave it like that for a second. And we can always work through it again. Clockwise? Yeah, I agree. Yeah, how do we get this? Let's say, okay, as the bar, this blue segment, moves down the rail, we include more of the magnetic field in the loop. Right? More of those field lines pass through the rectangular loop that we're looking at. Okay. Now, Lenz's law tells us nature doesn't like that. If it sees an increase, it will try to oppose that increase. It's another variation of Lenz's law. Nature abhors a change. If it sees an increased amount of field going through the loop, it wants to decrease that. Which means, oh wait, do I have this? See, I should have like a presenter view up so I can actually see. Yeah. Okay. So I don't have this, so good. As the bar moves down the line, there will be an induced magnetic field, okay, or I can't write anything. Let's try that one more time. There will be an induced magnetic field, I'll just call it the induced, going into the board. Right? The bar moves down, there's more magnetic field lines passing through the loop, an increase out of the board. Nature says, I don't like that. I will induce a current going into the, or excuse me, induce a field going into the board. And then we're left with, to produce a field going into the board, which way does the current have to run? And that's where we get our clockwise. Okay. You think of, kind of grabbing the bottom part of this bar, curling your fingers over, and it'll point into the board inside that loop. So to produce this induced field to oppose the change, the induced current, so now I got to be careful, right? The original current, the applied current, is going this way. Call it applied. And then because of this induced magnetic field, there is an induced current that runs the opposite way. But IND. Sorry, that's a terrible I. Now thinking about that induced current, I'm not worried about the applied current. Thinking about that induced current for a moment. You have this induced current and you have this external magnetic field. Which way is the force due to the external magnetic field on the induced current? Which way does that force point? Again, I'll say it again. Which way does the force due to the external magnetic field on the induced current point? Go ahead, get an idea. So you have the induced current going clockwise through the circuit. You have an external magnetic field pointing out at you. Which way is the force?
Survey says.
Outward from the middle loop.
I'm sorry?
Outward from the middle loop.
Outward from the middle of the loop. Walk me through.
Well, I was in right hand.
Okay, okay.
Well, you said on the current engine.
Yeah, on the current, yeah.
Never mind.
Okay, no, that's always good though, right? Like, hey, explain to me verbally. Oh, wait, okay, so you've identified, okay, yeah. Yeah, let's check it. Force, we need the direction of the current. That's our fingers. Right, direction of the induced current. Okay. So through this part, you could think of the induced current as going down. The force is coming, or excuse me, the magnetic field is coming out of the board at you. So on this movable, excuse me, I should have said, I want it on the movable bar, not the rail, the movable bar. Current's going down, the magnetic field's coming out at you. The force acting on that, the current flowing through that bar is going to the left. My right, your left. Let's go ahead and write that on, okay? So let's see, the force of the magnetic field on the induced current is to the left. Of course, I'll put up here, the force of the magnetic field due to the original current, the applied current, is to the right. So the instant I throw the switch, this applied current causes the bar to start accelerating to the right. As the bar accelerates, as it speeds up, the induced current gets larger, right? If this bar speeds up faster down the line, the flux through the loop is increasing at a faster rate. Because of that increased flux, the induced current increases at a faster rate. And when does the bar stop accelerating? Should ask that. When the induced current equals the original applied current. In other words, how much current is moving through the bar at that point? If this current equals that current. Zero. Yeah. They make the chamber, so that if we go back to this railgun idea, the chamber is long enough so that you can get the projectile up to a high speed. But there is some optimal, if they make it any longer, that won't actually speed up the projectile. So there's an optimization thing. If we get it too long, then the induced current will end up equaling the applied current, and then the object won't accelerate any further. So there's no added benefit to making the railgun, 50 miles long. So my guess is that they've optimized it. They figured out, okay, how long does it need to be to get a high speed, a huge acceleration and get up to a high speed? But then any longer than that's just wasted energy, wasted effort, materials, et cetera, et cetera. Yay, nay? So the act of changing the flux actually wants to slow down the object. Yeah. This is sometimes, well, yeah, let's do another one. Actually, you do something like this as well. Yeah, let's do another one. Same idea though. Hey, let's say I have a magnetic field region where it's coming out of the board, and I decide to push a loop into it. Loop a wire. Pushing it in. Okay. Yeah, let's start off with this. Which way will the induced current flow? If I take this square loop of wire and I push it into the field, which way will the induced current flow? I think we'll get your answer today. Okay. It's always fun. And notice it's not by accident. I mean for this region to have the magnetic field, and there's no magnetic field out here. And so that's not by accident. I meant for no field over here on the right-hand side. Oh, I should make sure I know the answer too. That's right. Which way does it flow? I'm taking this coil and I'm trying to push it into the field. Which way does the induced current flow?
Does the gray arrow, does that represent force?
Yeah, the direction of motion, excuse me. Yeah. So, yeah, let's say, yeah, I guess I was thinking the velocity here. No, might be changing, might not be. I guess you could think of it as the direction of the force, the applied, the external force. Yeah. But yeah, I'm trying to push this loop in. What direction does the induced current flow? Let's start with that. Am I increasing the number of magnetic field lines going through your loop, or am I decreasing it? I'm increasing, right? As I push this loop into the magnetic field, I'm increasing the number of field lines that go through that loop, the number of dots inside the rectangle. Another way of thinking about it. So as I jam this in, I'm increasing the number of magnetic field lines that go through my loop. So my loop will want to generate a magnetic field that points in which direction? Does it like that change, or does it not like that change? Doesn't. So if I have more magnetic field lines going this way through the loop, the induced field will point into the board. I don't like the fact that there are more lines pointing out through the loop. I will induce a field going into the board. So again, here the magnetic field that's induced will be into the board. Well, what direction does the current need to flow in order to produce a field into the board? Clockwise. Okay, yeah, I'll take it. Yeah, so you're thinking up right here? Yeah, okay. So red lines, make sure I got this. Yeah, into the board, yeah, good. All right, you think about grabbing that bottom wire, and again, okay, good, that works. And it doesn't matter where you do it. No. Yeah, good. So again, we have our current flowing clockwise. What's the direction of the magnetic force on the loop? Go ahead, talk to your neighbor. We now have the direction of the induced current. We have it going clockwise. I induced. So I'm just labeling I induced here. I induced. Okay. What's the direction of the magnetic force on the loop as I shove the loop in? So I'm not worried about me, the force that I exert on the loop. Right now I'm only worried about what is the force of the magnetic field on the loop as I try to shove it in. Go ahead, get an idea. Go. Okay. Put this back on here as a reminder. Yep. I gotta be careful. We're going to get a couple of different segments started off. Amen.
So you use the induced field and the external field for your power.
That's a good question. Can the loop exert a net force on itself? No. And there's your answer. Which field should I use then?
External.
The external field. Yeah. I'm thinking of the loop as my system, and I'm thinking of that external field as being the surroundings. So yes, this is why we also have to be careful about external and induced. I care about the external field acting on my system, not the induced field. Yep. Yeah. Well, okay. Yeah. You go. Okay, good. So now you're thinking, okay, let's shortcut. Yeah.
What are the conditions of the?
I'm sorry?
What are the conditions of the current through
The conditions?
the
What's? Sorry, the conditions of what? There's just a question about, you have two magnetic fields written out. You have the external field represented by the dots, and you have the induced field representing the response of your system to the surroundings. And so the question was, when you're calculating the force, which magnetic field do I need to consider? Do I need to consider the induced field, or do I need to consider the external field? The external field is the one that we want. Yeah. That was all that discussion was. The induced field is the induced field is due to the system, and a system cannot exert a net force on itself. Yeah. I'm going to go ahead, let's break this wire up into 4 segments. You say, why is Greg thinking about breaking this into 4 segments? I say, because there's 4 different directions for the current. Right? The current changes direction for each of those 4 segments, so I better consider each of these 4 segments separately. Okay? So I'll start off with the rightmost segment. What's the direction of the force due to the external magnetic field on that right piece. Or you can even give me a value if you want.
Towards the field.
Ah, yeah. Question. Is there an external field here? Survey says, I agree. If there were an external field, then yeah, we're good. But remember I said this is not by accident. I mean for the field to only be here. Over here, there is no field, which means what's the force on just this piece? 0. Yeah, it's just 0. It's 0 right there. There is no field. So, excuse me, on just this right piece, the force of the external magnetic field is 0. And if you're doing something, you probably want to say because B external is equal to 0, right? There is no magnetic field at this right location. Get rid of that one. Okay, so we don't need to worry about this piece at all. Well, how about, I don't know, what's your pleasure? Do you want the top wire or the bottom wire? Top? Okay. Let's get the direction of the force acting on the top wire. And notice I'm just talking about direction here for right now. I'm not worried about doing the calculation of the magnitude. Well, the current's going to the right. Our magnetic field is pointing out of the board. I'm going to rotate my palm. And so the force of the external magnetic field on the top wire is down. I'll go ahead and do that. So this one would be down. How about the bottom wire? What direction would that force be? Did I do something wrong? Yeah, it should.
Okay. Wait, so why did you? So you went like this instead of like this?
Yeah, either way, fingers in the direction of the current. Okay, now palm in the direction of the external magnetic field, which means I've got to rotate it so that it's now pointing out.
What is this?
Yeah, which direction is the external magnetic field? That way, but now you flipped your finger direction. There you go. Right, you gotta get your fingers in the direction of the current and rotate your palm to be in the direction of the external field. Which way is your thumb pointing? Down, which is the direction of the force. For just that top segment. I still have to do the bottom segment and the side segment still. So I'm just talking about that top wire right now.
So you used the external magnetic field system?
We use the external magnetic field for the whole thing. Yeah.
So we use the external magnetic field, but we're using the induced current.
Correct. You use the induced current, the current running through your system, and the external field, the interaction with the external field. Yes.
Is that the only current right now?
Yes. Yeah, for this one. Mm-hmm. So as you push this loop in, you start off, you can imagine starting way out here, and you push it where there's no external field, there's no current. And then right when that loop starts entering the field, all of a sudden an induced current will start flowing, and immediately a force will start acting on the loop. So it's weird, yeah, the presence of the magnetic field induces a current in the system, and because of that induced current, you also get a force acting on the system. Yeah. How about the bottom wire, the bottom segment? Which direction is the force just on the bottom segment? It's up. We again run our fingers in the direction of the current. We have to rotate our palm to be in the direction of the external magnetic field. and our thumb gives us the upwards direction. So on this bottom wire, it's upwards. What do I call this? FB bottom. And I'll call this the force of the magnetic field on the top wire. There we go, T. Next question for you. How does the magnitude of the force on the top wire compare to the magnitude of the force on the bottom wire? So we got the directions. How about the magnitudes? What's your gut tell you? They're the same. Why?
Because they're the same length and then they're the same amount in magnetic.
Yeah, say that. You hear that? The same amount of each wire is in the magnetic field. So you don't have to do any calculate. You could calculate. Greg would have to give you more numbers, right? Greg would have to tell you how long this wire is and how much is in the field. But just from the diagram, you say, well, there's a symmetric situation. The same amount of the top wire is in the field as in the bottom wire. So those two forces will be the same. We can get rid of that. So those two forces will cancel out. So I guess I'll put, maybe I should be more specific. The magnetic field on the left piece is 0. The magnetic field on the top piece is the same magnitude as the magnetic field on the bottom piece. So those two will cancel out. And so the last piece, of course, is the right piece. We run our fingers in the direction of current, flip our palm so that the magnetic field is pointing out, and we find that the force on this last piece is to the right. So what happens? As I force this loop into the field, what does the field try to do?
Push it out.
Push it out, right? As I try to force it in, the field tries to push it back out. Or a different way to say it, if I throw it and it's moving at a constant speed and trying to get into the field will cause it to stop, slow down. The reaction of the field as this loop gets presented is to decelerate, to slow down the loop. This is also sometimes referred to as, the application of this is referred to as magnetic braking, which we already saw. Sorry, I didn't bring the tubes into that. Right, we already saw that the tubes are another example of magnetic braking, using a field to slow down an object. Here's another example of that, using an object entering into a field to slow down the object. One of the cool things about magnetic braking, no mechanically moving parts. Right? Like bicycle brakes. How do bike brakes work? Or your car brakes for that matter? You should all go on a bicycle. Yeah, you ride your bicycle. You squeeze the handlebars. There's a cable going from the handlebar brake all the way down to your front tire. So when you squeeze, it shortens the cable, it pulls on the cable essentially. And what happens down by your front tire? Or your rear tire, depends. But front tire's left hand, rear tire's the right hand. I think they tend to do that because people tend to be right-handed as dominant hand. So you want to, if you're gonna brake hard, you want to brake hard on the rear tire. Right? I've only done it once. Only cost me 4 stitches. On the front tire. Hard brake on the front tire. 4 stitches. Okay. Safe. 4 stitches, right? Yeah, what happens? You pull the cable, it shortens up. What happens near your front tire? The brake clamps on the wheel. In other words, you shorten the cable, those brake pads press up against the wheel. That's a mechanical part. If you do that long enough, what happens to the brake pads? They wear out and you have to replace them. You take them down to Fitz's, they throw them new ones on. They recable your bike if it stretches out, et cetera, and you're off and running. The same thing happens in your car. It's just not a wire leading from, your brake pedal to the brake pads. It's a hydraulic cylinder, blah, 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 blah. The idea stays the same. You push down on the brake pedal, it transmits all the way to your brake pads, and literally, anybody change a tire recently? Jack up somebody's car and just take the tire off. If you take the tire off, there'll be a disc. It's called a rotor. Right, probably about the size of your head, maybe 8 inches, 10 inches in diameter, silverish. And in fact, you go out and look at your car, you can usually see the rotor through the hubs of the wheel. Okay, so if you see a circle behind your wheel, that's the rotor. And that's the part of the wheel that the brake pads press up against. So when you hit the brake pedal, there are brake pads in your brake assembly that press up against that rotor. That's how your car slows down. It's a mechanical it's literally friction slowing your car down. That's literally all it is. It's the friction between the brake pads in your car and the rotor. Now, of course, brake pads wear out. Because of that mechanical contact, they heat up. They tend to rub a little bit of layer off every time you brake. And eventually, they'll wear out. You'll have to get your brakes fixed. You'll have to get your brake pads changed out. And you know when that happens because manufacturers are smart. They put a little piece of metal in the brake pad. And when the brake pad wears down to a certain spot, that metal starts touching the rotor. So you get a metal-on-metal contact. That's that screeching sound. That is an audible warning that your brake pad is low. Take it in and get it changed. If you do it early enough, then it doesn't affect the rotor and you can keep going. You just change out the brake pads and everything's good. If you let it go long enough, you start gouging the rotor, and now, instead of doing a $60 brake pad change out, you've got to do a $150 rotor and brake pad change out. And oh, by the way, when you change your rotors, you got to do both sides. So if you damage the rotor on one side, you got to change the one on the other. So now you're up to 300 plus labor, et cetera, et cetera. It's a mechanical contact. Sorry, it's not like I haven't done that. And if it's really bad, you get a seized caliper. Don't get a seized caliper. If you hear squeaking from your car, usually it's like a $15 fix. Just do it. Anyway, this does not suffer from any of those problems. This is not based on a mechanical contact, which is kind of cool. Generally, magnetic braking, one of the advantages to it is that your pieces don't wear out. It's lower maintenance because there's less moving parts. Now, I think, for example, oh, that's to be continued. That's almost like what you were thinking. Okay, I'll have to think about this. Hybrid cars work slightly differently. And it's a little bit of this magnetic braking stuff, to be continued. Okay. But the one place I was thinking of that you see it, okay, yeah, we got this. Yeah, we got this. The place I was thinking of is right here. Okay. Sorry, let me blow that up so that everybody can see it. Let's see if I can do that manually. Sorry, we verbally walked through the rest of that stuff. Let's just blow this sucker up and from current slide. Did it do it? Maybe. Oh, don't crash on me. Oh, don't crash. Don't let me down. There we go. I just blew it up. You see it? It's green. Cool, right? You have no idea what I'm talking about, do you? Do you see these? Right? What you're looking at is a series of magnets on the side of a roller coaster cart. right? Roller coaster track. What you're looking at are a bunch of, now I don't know, I think they're permanent magnets. I'll have to double check, but I think they're permanent magnets. Because if they were electromagnets, then you'd always have to have power. And if your power fails while a roller coaster is going, that's dangerous. Right? So my guess is that these are permanent magnets, no external power supplies needed or anything like that. Okay. So what you're looking at magnets, and you can kind of see that they look like rectangles, right? You got one rectangle here, and then it's a little blurry, but it looks like a second rectangle, a third rectangle. You see that there's a bunch of, it's not like one solid magnet, it's a bunch of smaller magnets. Now, I don't know for sure, but my guess is, if we looked at this from like the above view, my guess is that we have a bunch of magnets in a row, something like this, and I'm guessing that it's a north pole, then a south pole, then a north pole, then a south pole, then a north pole, then a south pole. So it's back and forth. And of course, you've got the pair on the other side. This is like the overhead view. You okay so far? Kind of following me? So you can think of between, let me get this out of the small regions where the magnetic field changes direction. Okay. Now, what do you need? Take the roller coaster car. Put little metal fins on the outside. All right. Put little metal fins on the outside so that those metal fins pass right through those gaps. You basically, those metal fins are like taking a loop and pushing it into a magnetic field. So as the roller coaster car comes along the track, those little metal fins on the side go through those magnetic field regions. What's going to happen? The induced current in those little metal plates will cause the force of the magnetic field to slow the cart down. You're done. No moving parts required. Well, okay, the roller coaster cart's moving, but I mean, it's not like brake pads pressing up against something on the roller coaster cart, right? The roller coaster just goes through this magnetic field, those little fins on the side, and that automatically slows the cart down. And of course, you've got a series of them. Right. So you've got a series of them all the way through. I'd have to check to see why the gap is there. I don't know for sure. But you can see it kind of goes all the way through. And you notice that as you get further down, you use less of them. I'm guessing that's because it's not moving as fast anymore. No. Of course, yeah, you got the whole long train. I mean, yes, there's some other stuff. There's still some mechanical stuff, like some tires or a crash bar or something like that. But at the end of the day is that this is less moving parts. Less moving parts means less maintenance. Less maintenance means, more profit. I suspect that, like on those hybrid cars, it almost works the same way. There's one more thing going on, but it's somewhat similar. Yes?
So why would they be alternating?
Why would be alternating is so that the flux changes direction. Okay. So the issue is, one thing that's unsaid about this is, wait, what, huh? Oh, that's weird. Oh, okay, I see. I put it on top. One of the things that's unsaid about this process, let me get this out of the way so that we can see it again. One of the things that I haven't mentioned, I mentioned it was really important for this side not to be in the external field. If this side is not in the external field, the force on this piece is 0. And so you have a net force pushing to the right. What would happen if the thing was all the way in the field? Let's say this loop keeps moving until it's all the way in the external field. It's a good question. Let's say the loop is fully in the external field. As the loop continues moving in the external field, does the amount of field lines going through the loop change? Survey says no. Which means what's the induced current running through the loop? 0. Which means what's the net force acting on the loop? 0. There's the answer to your question. Once it goes all the way into the field, the induced current drops back down to 0. Incidentally, let's say it hits the edge of the field and it starts exiting. You will again get an induced current, and again, that induced current will try to prevent it from leaving the field. Okay. So entering, it tries to slow it down. Once it's in the field, it'll be a constant speed. Exiting, it'll try to slow it down again. So that's why they do that series of north, south, north, south. You're presenting a bunch of areas where all of a sudden it enters and exits, enters and exits. And so you get a better braking efficiency. Yeah. It's a bunch of magnetic speed bumps. Instead of just having one, going up a bump and staying up at a higher level, this one goes up, down, a bunch of speed bumps in a row. Theoretically speaking, this is also supposed to give a smoother braking experience. I'm not a fan of roller coasters. Of what? Whiplash, yeah. Let's see, what the last roller coaster I was on was probably Space Mountain about a decade ago. And I got so terribly disoriented. I was walking, I didn't throw up, but I felt like I was walking around Disney World like this for like an hour. Something about the darkness and just, I'm done.
It was like 30 miles an hour.
Oh, I know, but when you can't see the turns coming up, it feels a lot faster than that. Yeah, right? Like you can't even prepare your body. You don't know if it's a left turn or a right turn. I was so disoriented. Nowadays the kids put me on the swing and swing me around and I'm like, I'm done. I can't do it. Like, swing while you're young, because, once you lose it, it's gone. While you're at it, go home, put your ear to your shoulder and spin on a chair. If you haven't done that already. While I'm talking, no? Are you? Instead of doing this and getting dizzy left, right, put your shoulder to your ear and spin. It screws up a different set of tubes so that when you stand up, you get dizzy forward, backwards instead. You've never heard of this? Oh, you should try it sometime. Go to your dorm room, put your head, and then just spin. And just be ready, because the time I did it to my mom, she BAM! It was great. Like, Mom, you're gonna feel a little wheezy back and forth. Oh, I got it, okay. BAM! Awesome. It's so sick. That's why. Yeah, good question. So once the change disappears, then your braking disappears as well. I'm sure there's other good places. Like I said, I think I have to double check to see if hybrid vehicles use this or not. There's certainly a magnetic piece to it, just the one we'll talk about next. There's certainly a magnetic piece to it, but I just don't know if there's a mechanical connection or if it's purely magnetic and nothing else. So yeah, this is a really cool place to do it. Nope, I'll leave it at that. So we've talked about changing the magnetic field strength. So one way to change the flux is to change the magnetic field strength. Say, for example, the distance the magnet is from the coil of wire. The second way that we talked about changing the magnetic flux is increasing the area. Right, that would be like the railgun. You increase the area, the magnetic flux goes up, you get a response current that tries to oppose that increase. The third way that we can do this, changing the flux, is you can keep the magnetic field constant, you can keep the area constant, and you can simply change the angle between the area and the magnetic field. So what do we have here? Think of a loop of wire, but it's a top-down view. So I've got a pivot point here in the center, and shoot, excuse me. I was thinking of the wire rotating, the bottom side's going to the right, the top side's going to the left, and it looks like I have shamelessly included some current. Oh, I've got them all together too. I have shamelessly, ignore the dot and the X. My animations are off. Okay. So you have a loop of wire. You can think of a square loop of wire or a rectangle, and it's pivoting this way. It's going like this as seen from above. So now we're changing the angle. We're changing the amount of flux by varying the angle. Different way, yeah. So yes, we're back in the desert. We're back in the desert and it's raining, and I'm doing this. Right? There are some times where I catch some, but there are other times where I catch none. If it's falling this way. So that's what we're doing here. There we go. Okay, pick up my mess. Pick up my mess. For the position that's shown. So for the orientation that's shown, the flux through the loop. Okay, for the orientation that's shown and the motion that's shown, is the flux going to be increasing or decreasing right after this instant in time? So I've got it right here. Some instant in time later, will the flux have gone up or gone down? Goes down. Right now, this instant that I've shown you, the cup is going to catch all of the rain. An instant later, if I angle the cup just a little bit, I'm not going to catch as much rain. Okay. It's raining magnetic field. I have the surface of my cup. If I rotate that, it's going to catch a little less, and a little less, and a little less, and eventually none at all. So that for this brief instant in time, the amount of magnetic field that passes through is going to start decreasing. Which way should the induced magnetic field point then? If there's slightly less magnetic field lines going through my area. I'm sorry? The same as the external. Yeah. If I rotate this and less field lines get through, that means that my induced field should start pointing in this direction. Be induced. Be induced. Be induced. Be induced. I guess I could just start saying bind. Okay. Neither seem to be catchy. Okay, someday. Yeah, because of this twisting motion of the loop, less of the external field goes through the loop, and therefore Lenz's law tells us an induced field should try to compensate. Well, based on the direction of that induced field, well, I'm so glad. Right? I'm glad I told you to ignore the dots and the X's. Right? Which way should the current be flowing if the induced field is pointing to the right? Excuse me, the left. And remember, this wire is kind of coming out at you and going down and going back in. Right? This is a rectangular wire coming out of the board. That helps you. Something like this. There you go. We're spinning it like that. Nor my shamefulness. In order to produce an induced field going to the left, what direction should the current be flowing on this top segment of the bar that's coming? Did I use it right? Yeah. Which way should the current flow on this top bar? Oh, okay, I'll buy that. Yeah, so you're saying it should be going this way. Yeah, I'll buy that. Right, we can grab that top piece, curl our fingers, and get the induced field going that way. Good. So, which means if it's going this way, it should be going into the board up here, and it should be going out of the board up here. Which is what I said, ignore my indiscretions. Don't air dirty laundry in public. I'm sorry that you had to witness that. No. Thank you. Isaiah's looking at me like I'm crazy. And again, we could check this wire going in, okay, yeah, the induced current, the wire coming out, okay, good. So we get an induced current going to the, well, this way. There we go. Questions so far? Yeah, it should be coming out, up, going back in, coming down, coming out. Yeah. So counterclockwise as seen from my perspective. There we go. That doesn't right here. Yeah. Now we can imagine for a second, as this, I put it down and then I put my prop down. So you can imagine for a second, as this thing rotates, keeps rotating, the induced field is going to keep trying to get an induced field this way. Eventually it goes here. No flux. There are no magnetic field lines passing through my area. Instant later. Now what is it going to want to do? I went from 0 to non-zero. Which way is the induced field going to point now? Pointing to the left, pointing to the left, pointing to the left, because the flux is decreasing. I hit 0 flux. Now my flux starts increasing. Do I like that increase? No. So which way is the induced field going to point now? Is it going to keep pointing to the left? Survey says, no, it's going to start pointing to the right. It's going to flip directions. You hit this 0 point where there's 0 flux. Now the flux increases. The number of lines that goes through my area starts increasing. Well, I don't like that increase. It's, more field lines going this way. I don't like that, so I'll induce a magnetic field going that way to try to oppose that increase as it increases. Which means, what happens to the current flowing through this loop? It starts out flowing this way, but at some point, what happens? It starts flowing the opposite way. Right when the loop hits here, the current stops and starts flowing the opposite way. Of course, right here, you hit maximum flux. Right? When the face is, again, pointing with the magnetic field, you hit maximum flux. Then what happens to the induced field? Here it's maximized. I go a little bit further, now it's decreasing. It doesn't like that decrease, so now it'll do an external field this way. So the current switches direction again. Decreases, hits 0, now it's increasing. Yeah,
So is this an AC current involved?
That's exactly what this is. I said, hey, I would skip Faraday's law altogether, except for the fact that all of our electricity generation is based off of essentially this concept. When you take a loop and you spin it in a magnetic field, because you're decreasing, like I said, decreasing the flux, the current flows one way. Excuse me, this way. Then increase, the current flows the other way. Then it starts decreasing, goes the other way. Then it starts increasing, goes the other way. And you get a current that oscillates. We call that an alternating current. Dynamite! Okay, good. I don't know if that's the origins of their name, but it sounds good. Right? AC alternating current, DC direct current, like a battery. I started singing that in last class, and somebody said, TNT? I'm like, by who? And they're like, TNT? And then he called me old. Yeah, I know. He didn't do it directly. I said, AC/DC. He goes, oh, my dad has that CD. I'm like, thanks for calling me old, dude.
So we did it alternating one.
Is that sorry?
So we did it alternating one.
The alternating one?
You said he didn't call you that directly. So
that was really bad. Oh, that was, man. I have to try to figure out how to put that one in my repertoire. It seems like a good rumor joke. On the lines of, why do they put fences around cemeteries? Because people are dying to get in. Thank you. I'll be here all week. No? Okay. Yeah, this is the exact origin of an alternating current. In fact, if we go down to Clifty Falls power plant, pretty much, I can think of one example, but pretty much everything else that deals with power, electricity generation, is using this concept. Take a wire, spin it in a magnetic field. The question is, how do you spin the wire? Because you now know, we won't go through it, but if I start spinning the wire and I start looking at the torque, if I look at the torque of the external magnetic field on the spinning wire, what do you think that torque is going to try to do? We could do it. We could go through and extrapolate, but you already know what it's going to do based on the rest of the conversation from this lecture. What's it going to try to do? What's the external magnetic field going to do if I take a loop of wire and try to push it into the field? Push back. It's going to try to get it back to the status quo. It's going to try to slow it down. What do you think the external magnetic field is going to do if I take a coil of wire and start spinning it? What do you think it's going to try to do? Stop spinning it. It's going to try to slow down. The torque will act to try to slow down the spinning motion. So again, it's the same thing. Unfortunately, I can't just take a coil of wire, spin it in a magnetic field, and just get current out of that. That would be nice, right? Just spin it, walk away. That's my infinite source of current. Unfortunately, it doesn't work like that. The spinning motion, the kinetic energy of the spinning motion gets converted into a current. They sometimes say electrical energy. The spinning of the loop, the kinetic energy, decreases at the expense of driving current through the circuit. So you're literally looking at transferring kinetic energy into electricity. So again, we spin this loop in a magnetic field. The loop inherently wants to slow down, which means we have to hook something up to the loop to keep it spinning. What do we usually hook up to the loop? Thinking of like Clifty Falls State Power Plant, for example, or maybe it's not State Power Plant, but Clifty Falls Power Plant. What do you hook up to the loop? If anybody's been in northern Indiana, anybody done 65 to Chicago anytime lately? Tippecanoe County, and north of Tippecanoe County, there's a huge wind farm. There's also one in Kokomo area around Windfall. Okay. How do you get how do you spin the coil? Okay, so current from the waterfall. One way to do it was go to Hoover Dam, and what do? Well, you take a huge thing of water, a reservoir, you give it a small little chute that it can flow down, and in that chute, you put what's called a turbine, turbine. Is that one of those like that's spelled the same but it's pronounced differently? No, is there an E on the end? Okay, it's like wind and wind. It's not like wind and wine, or minute and minute. They're spelled the same, they're pronounced different. Okay, anyway. Okay, so you take this water, you give it some access chute, and then you put a turbine. So essentially it's like a fan blade attached to a shaft. Water hits the turbine, spins the fan blade. Guess what's on the other side of the shaft? Let's put a coil of wire. Take a coil of wire, put it between a magnetic field. Let's put a horseshoe magnet in here. You know, something like this. So as water hits the turbine, it spins. That spins the shaft, which spins the coil in the magnetic field. Boom, there's your electricity. Of course, the coil wants to slow down, so you have to continually dump more water. Or up around Kokomo area, the wind farm. Instead of water, it's just the air, right? Those windmills, you're essentially looking at the blades of the turbine. Inside that big bus housing on the top of the 300-foot pole, there's a coil of wire and magnets. It's spinning the coil of wire in the magnetic field, and then the electricity is produced that goes down the wire into the substation.
How do you store that energy?
Oh, so that's one of the interests. I don't know very much about this, but this is one of the very difficult problems, is that you want to match your electricity production with demand. There's not a very good way of storing the electricity, which leads to some issues like if it's summer and you have an unexpected jump in temperature, unexpectedly, you usually have people use more electricity. Well, more electricity, that means that you need more of your power stations to generate more electricity. And unfortunately, our demand generally spikes before the power stations can respond. And then you get things like brownouts, where the demand is higher than the production, and so some people don't get electricity. And it puts a strain on the system and yada, yada, yada. Yeah. So that's a difficult problem. It's not easy to store that excess electricity once it's been produced. So usually what you do is if you need less electricity, for example, on a hydroelectric, you just don't let as much water through. Or if you need more electricity, then you open up the floodgates and, you know, push as much water through the turbines as you can. It's a little easier for hydro. Wind, not so much, right? Either the wind's blowing or it's not blowing. So usually what happens is on windy days, where the windmills produce more electricity, other forms of electricity tend to decrease. So Clifty Fall doesn't burn as much coal. There's already an excess of electricity on the grid, so Clifty Falls doesn't have to put as much onto it. You know, things like that. That's actually a real big problem in California right now. It's called the duck curve. Okay? So what happens, California has a lot of solar. So if you look at a coal-fired power plant in California, if you plot its like the electricity as a function of time during the course of a day, you'll get something where it's high, 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 then it drops down to being really low, and then it spikes back up. It's called a duck curve because it's supposed to look like the outline of a duck. The head going down to the back and then back up to the tail. And it's a real big issue. What's happening right here? Say this is the energy output of a power plant in California, a coal-fired power plant. Why is demand high right here and right here, but it's low, say, in the middle of the day? Why would energy demand, why would there be less need to produce energy via a coal-fired power plant in the daytime? There's more light, which means during the daytime, more light, you have more solar power. You have more energy being produced via solar power. So one of the problems that California is dealing with is that their plants are working really hard at nighttime, and then they shut them down during the day, and then they have to reopen them in the evening. That cycling is hard on the plants. The power plants, like wear and tear. So energy storage is a huge problem. Tesla does it by doing batteries, basically. We'll store all this excess solar energy and we'll pump it into a battery. And then when the nighttime rolls around, we'll just pull the energy from the battery instead. But if you can figure out a way to store this energy, then yeah, you can make bank. All other, Clifty Falls, how they turn the turbine? Boil water. Right? They take water, they turn it into steam, the steam rises, it hits the fan of the turbine fan blades, spins the shaft, and that spins the coil. So how do you boil the water? You burn coal, right? Literally, you're just burning coal to boil water. Or a nuclear power plant. Instead of burning coal, it's nuclear fission of uranium. That heats the water, causes it to boil, that turns the turbine. So, geothermal. Geothermal? You sink pipes into the ground, fill it with water, and the interior heat of the earth causes the water to boil. And you use that steam to turn a turbine. The only thing that I can think of where you don't use this idea to generate electricity is solar power. Solar power is the only thing I can think of that doesn't rely on this. And incidentally, solar power, that's another interesting problem. Solar power produces a direct current. And guess what? Everything in our house is used to. Alternating. So one of the most expensive parts of a solar panel is the converter, the thing that takes the DC from the solar panel and turns it into AC so that your house can use it. Which is ironic because this computer, you know what this brick does? Takes AC back to DC. Yeah, anyway. Hey, have a good weekend. I'll see you Monday. Thanks for your attention.